Hello, everyone. We are waiting for everybody to join. Good afternoon, everyone. Welcome to session 14A, Risk, Vulnerability, and Relocation. We have 5 talks for you today, actually 6. We are very excited with the speakers we have today. And we'll start with the first talk by David Williams from Istanbul Policy Center. And his talk is Enhancing the Inclusion of Vulnerable Communities in Adaptation Planning. Please welcome, David.
Thank you very much. I hope everyone can hear me okay and can see my screen okay. First, a sentence on myself. I'm David. I'm really happy to be here. It's really great that this conference has been managed to be organized despite the current conditions, which I'm sure wasn't an easy feat. So thank you very much to all the organizers, and thank you very much for the introduction. I'm a geographer. So my background, my academic background is in geography, but I then conducted a PhD in political science, and at the moment I'm conducting a research fellowship at the Istanbul Policy Center, which is part of the Sabancı University in Istanbul. And what I'm basically researching is how to ensure that the relocation of communities is a last resort and remains a last resort. And one way to do that is by enhancing the inclusion of vulnerable communities in adaptation planning. Now, we've been hearing a lot at this conference about who is primarily affected by climate change. It's primarily vulnerable and marginalized communities. And this is also the case for urban areas. So we're having this dynamic, particularly across low-income regions, where you have people living in rural areas coming to the city in search of jobs, in search of healthcare, in search of education, but space being very limited in cities, and that's why people are settling in more and more environmentally hazardous areas, because basically that's where no one else is living. At the same time, you have the increasing impacts of climate change, the increasing intensity and frequency of extreme events, which is causing a real issue for vulnerable communities in urban areas. And this is also the case for Istanbul. And it's why Ekrem İmamoğlu, who is the mayor of Istanbul, proclaimed at the Climate Adaptation Summit earlier this year that to be a resilient city, we need to find inclusive and sustainable solutions for future problems today. And the urgency of the issue becomes quite clear when you have a look at the European coastal cities most vulnerable, or rather with the projected largest annual average losses for the coming years. And as you can see, Istanbul is the top of that list. The issues facing Istanbul, well, it's drought, it's heat waves. Today was a very hot day. It's evening time here, of course. And forest fires are becoming an increasing problem. But then, of course, you have increasing heavy precipitation events causing landslides, causing riverine flooding, pluvial flooding, and also sea level rise causing coastal flooding. The issue of spatial segregation in Istanbul is very much reminiscent of other global cities where spatial segregation and inequities are emphasized and become more acute. These new ghettos are profoundly influenced by internal and international migration. Most excluded people are primarily migrants, both old and new, and people displaced from one neighborhood to another in Istanbul, or from other areas, in particular from the Kurdish region. With 63% of its current population born elsewhere, Istanbul is still a city of migrants. And I think this is the case for many global cities. So what I did was I used Istanbul as a case study. And I used the theory of urban adaptation justice, which proposes 4 criteria: participation, to what degree are local people involved in decision-making relating to climate change adaptation; capacity enhancement, to what degree do local decision makers have access to workshops and to sort of learning measures that can enhance their ability to deal with climate change. Governance, that's particularly the concept of multi-level governance. How well does the local government level work with regional and national government? And then finally, justice integration in urban planning, which is specifically, to what degree are adaptation measures tailored to those most vulnerable communities? And then I compared and contrasted this with the fundamental elements of effective local adaptation policy. So basically, any effective local adaptation policy needs to have a goal, like an overall objective, a target, which is more of a numerical a value with which you can measure progress on this goal, instruments, so tools and mechanisms with which to achieve the overall objective, and an agent who's going to develop and implement these mechanisms. And what I did was I took 5 policy documents, both from the national and the local level, and I checked, for participation, is there a goal for participation? Are there instruments suggested for governance? Are there specific targets? Are there agents suggested to carry out these workshops? And I came up with this. So I'm not going to go into the detail here too much on this slide. I just want you to sort of take away that participation seems to be working quite sort of okay. Capacity enhancement, yeah, it's being mentioned quite a lot in the policy documents. Governance, so-so. And justice integration seems to be a bit of a disaster. So let's go into a bit more detail. So participation, yeah, there were goals. This was mentioned as an objective in all the policy documents. No targets, unfortunately. Instruments, again, seem quite positive. Agents, a couple were mentioned. For capacity enhancement, again, they all acknowledge that it's an objective. However, targets not so much. A couple of instruments and agents were covered quite well. Governance, again, goals and instruments and agents were mentioned, no targets, unfortunately. And justice integration and spatial planning, well, I already said it was a bit of a disaster. And yeah, it was mentioned as a goal twice, but apart from that, not mentioned at all. Okay, so that's nice. We've collected our data, but now, of course, comes the hard part, which is going into the effectiveness of local governance and taking these results to the local municipality and sort of trying to suggest ways of going forward. Okay, so there we go. And basically, I take all my data, I take the published policy briefs, I take the paper which has been submitted to a journal, I get on my cape, I do my hair, I get my mantras together. Climate change is happening much faster than predicted. Cost of inaction is so much higher. Adapting to climate change can be used as a vehicle for so many other benefits. Every small change helps, and in years to come, this is going to be a huge issue. And then I turn up at the municipality, and I am confronted with this reality. I don't know if many of you are aware of this issue, but it's basically it's a very nice illustration of the priority problem, which is in essence, for just adaptation to be a priority, it needs to be embedded within the climate change adaptation priority. Okay, so climate change adaptation in itself needs to be prioritized at the local level. That needs to be embedded within a climate change priority, and that, again, in the case of Istanbul, needs to be embedded within an everything else priority in a city of 17 million people with the next earthquake 10 to 50 to 100 years overdue, depending on which experts you believe. So what I'm going to show to you now is basically a after lots of wrangling, after lots of discussions, are going to be 4 bullet points on measures which were deemed feasible in a city the size of Istanbul. The first one is to conduct vulnerability assessments to identify vulnerable communities. Currently in the city, we don't actually know where vulnerable communities are located and what determines their vulnerability. These assessments haven't been carried out, and it has been agreed upon that this can be evaluated as a feasible measure. The second
2 minutes.
Yeah, thank you very much. The second policy recommendation, which was to include the identified vulnerable communities in the development of plans, policies, and practices, reflecting their socio-spatial vulnerability, and coming up with ways to actually try and ensure a just inclusion. I mean, not just carrying out the odd workshop and then ticking the box on participation, but actually involving them in the whole process from beginning to end. Then, third of all, is to install climate change officers to encourage cross-departmental collaboration. This has been very effective in other big cities, and because climate change adaptation is such a cross-departmental issue, you need these sort of these linking linking agents to encourage collaboration between the departments. And finally, awareness raising, particularly for the importance at national level. Okay, because what you find in many places is that the problem is actually really local people are aware of the problem. Local people are affected by the problem, but it's not perceived that way at the national level. So awareness raising can be really effective in this. These are all mainly focused around Istanbul, but sometimes I have friends ask me as well, what can average citizens do? What are sort of more broader ideas for addressing this issue? There I normally name 3 things. One is to vote for the appropriate parties, of course. The other would be to better protect and support organizations working with vulnerable groups. That's particularly more in more authoritarian contexts. That's been shown as one of the most effective ways to support local communities themselves, is to support the groups working with those communities. And finally, it's transformative anti-racism. It's acknowledging where marginality and vulnerability stem from, and that it's handed down through generations. It's not a problem that has been around since yesterday, and this the intersectionality of the issue really needs to be taken into account. That's it from me. If you have any questions, there might be some time now. If not, I'll happily wait until the end. Thank you very much.
I don't see any questions in the chat, and you are perfectly timed, so I think we'll leave more questions for afterwards. So now we move to the second talk, which is Integrated Climate Risk Assessment and Hyperlocal Approaches to Climate Adaptation for South Florida by Tyler Harrison from University of Miami. Tyler? I can't hear you if you're speaking.
Let's try that. Okay. So many buttons these days. Sorry. So my name is Tyler Harrison. I'm presenting on behalf of an amazing team of academics from the University of Miami and community organizers from Miami-Dade on a project on integrated climate risk assessment and hyperlocal approaches to climate adaptation for South Florida. 2 years ago, we presented on some formative work we were doing on this, and for this time around, we've been able to really get into some details on the mapping and integrated risk assessments, as well as working in 2 specific communities in Miami-Dade. And we'll talk a little bit about both of those approaches as we go forward. Our specific partners are the Clio Institute, Catalyst Miami, Miami-Dade County, and City of Miami Offices of Resilience. And our work is sponsored by the University of Miami ULink, which is focused on interdisciplinary research projects to address grand challenges, and also by AT&T Argonne Laboratories, which has been very useful for helping us with the data integration across our mapping part of the progress. So very much like David's, we've got a goal of really trying to focus on vulnerable communities, get them more engaged in the decision-making process, and think about ways we can engage in adaptation that is different from the top-down infrastructure-based approaches we typically see in a city like Miami. And as 3 parts of that, what we've got is the integrated climate risk assessment is focusing on other ways of assessing vulnerability besides the typical sea level rise that you would think of Miami, and looking at things like the social risks and vulnerabilities, the built environment, as well as various physical risks across that. And I'll talk in detail about how we've done some of that process of assessing vulnerability for these communities. The second is then going into our communities themselves, working with our partner organizations and getting community members involved through a process of Photovoice, where they take pictures of their experience of climate change within their communities, and then design thinking, where they imagine the best possible future for their communities and build out solutions, and then ultimately present them to policymakers within the city and county of Miami. And then finally, we were really interested in whether or not this approach actually has the possibility of increasing individual or community capacity through the learning of skills, the engagement in policymaking, and so on. And so we've measured those through some surveys. I'll talk about each of these in some detail, but it may be a pretty high overview since we've only got 12 minutes to get through all of this material. The communities that we chose for this particular set are both in Miami-Dade County. And so these visuals up here, this is the entirety of Miami-Dade County. And then Little River and Homestead are the 2 communities we were working in specifically. And Little River is northeast Miami. As you can see, it's partly coastal, but also goes inland across I-95. If anybody of you have driven I-95, you know just how dense and urban those possible areas are. Homestead is more in the southwest of Miami-Dade, and it's much more agricultural. Both are very diverse in terms of population, and both are perceived to have high near-term vulnerability to climate change. And these are also areas where our partner organizations were working, which makes them ideal cases to try out this process and see what we're able to accomplish. As we begin by looking at the data integration, the data for the maps came from Argonne National Labs, Esri, and Miami-Dade County. They came in all different formats, so there's some transformation that had to occur. But for this project, we focused on 8 different layers, which is bare earth topography, greenness, heat, hydrology, access to air conditioning, housing year built, wealth distribution, and septic systems. I'll put these up in a little bit larger format so you can get a better sense of them, talk about how we used them and how we integrated them. So if we start with bare earth topography, you can see these slightly darker green areas that run along the water and this riverfront in this area here are sitting at about 2 feet of elevation. As we move to this brighter pink, we're only up to about 10 or 12 feet of elevation. So all very low, but much more flood risk in that darker green area. As we look at hydrology, we can see that this is not only the floodplains from FEMA, but also groundwater contours. Again, much more risk right along the coastal area and in this inland area along the canal and the river itself. These maps also contain a variety of different kinds of information that we shared with participants when we got into the community, so they could try and assess their own sets of risks and make sense out of what kind of data they were seeing within their own communities. Right now, these maps are focused on Little River, but we've also done them for Homestead as well as the entirety of Miami-Dade County at this point. If we look at heat, we can see that this darker purple area these are measuring surface temperatures. The purple is about 99 degrees, the blue is 116. As we move over to the dark orange, it's about 136 degrees surface temperature. So heat is very much a problem here in Miami as part of this process. If we look at greenness, the darker orange is tree canopy, the yellow is less tree canopy. The white blocks on top are vectors that represent the distance that any household has to go to get to their nearest park to have some shade or greenery. And finally, if we look at access on this slide to air conditioning, we see we have much more access in the dark blue, which is along the coast, which ironically is the coolest part, less access here on this inner part where we have the most extreme kinds of heat. And for the last set of these maps, if we look at housing year built, the darker oranges are older, for Miami standards anyway, which is around 1950. And very few houses here are up to current hurricane codes like these dark yellow yellow buildings here, which means this whole area is an older community in Miami and highly at risk for hurricane damage, for example. Miami also has extreme wealth inequalities. If we look at this red line here, this is actually part of the redlining that occurred in 1937. And we see the effects of that carrying forward, where we still see extreme poverty in a lot of this area, as well as higher populations of Black-owned homes and businesses. Along the coast, where it's green, they didn't have the redlining, much more affluent populations. And finally, for those who may not be familiar with Miami, we have a different kind of risk that we're built on a very porous oolitic structure, which means it's not just sea level rise coming in from the ocean that's a problem, but rising up from underneath that is a problem. These areas that have fewer dots have less septic systems. These with more dots have more, which means they're more at risk of sewage coming up as sea level rise goes from the bottom up. Now, as we look at all of these maps, we can see there's a lot of different types of risk and vulnerability in just this one community. How do we make sense out of this to identify things that need to be done and what the ultimate risk of that community is? Using just 3 of these different types of maps as an example, we took the data and converted it to having a similar resolution of 10 meters per data point and reclassified them to a common scale of 1 to 5, with 5 being the high risk, put them into an algorithm of equal weight at this point, and you can see these darker red areas are the highest areas of risk. So some of the coast is more at risk, but a lot of it is not. And this inland area where we have the combination of socioeconomic challenges, low elevation and high heat becomes some of our highest areas of risk. Currently, we've done this kind of mapping for 20 different levels of data for the entire Miami-Dade County, and we're working with both our community partners, community members, and government experts to find the best way to map and score vulnerabilities for different communities, with the recognition that there will be different challenges in how we adapt to climate for each of them. From there, we took that data and we went to the neighborhoods and got community members involved in a process of community engagement with Photovoice and design thinking. And I don't have time to go through all of the beautiful stories that they told, but Photovoice, they take the pictures, they create their narratives, and they tell us what they see happening in there. And you can see they come up with some really beautiful kinds of stories oftentimes about really tragic kinds of things. For example, the one on this sign here about all of the building that's happening and working in the warm weather. And this one on the far right of this tree, this is a rare exception of a positive thing where there was actually shade over a bus stop, where the majority of places in Little River have no shade, and you're talking 136 degrees surface temperature. Everyday adaptation becomes a challenge. If we look to see, are there differences across our communities, when we move to Homestead, we see they have some similar themes. They're still worried about storms and flooding, but there's a lot more focus on agriculture and the ecosystem. If they're talking about extreme heat, it's more about the farm workers and the agriculture, and a lot more concern about daily sustainability and trash. There's a number of the dumps for Miami down in this part of the county, and it affects everyday life in different kinds of ways. And so really testing our assumptions that that hyperlocal approach is very different. We see very shared common themes, but if we get deeper, we see very different sub-themes. So flooding, the emphasis on ability to get to work, but in Homestead, it's more about agriculture, extreme heat, and human impact on things, for example. Once they told us about their everyday experiences, we took them to design thinking and moved through the process of discover where they focused on those daily experiences, moved to framing the 3 leading challenges. For example, this one was flooding, lack of shelter from extreme heat, and proper housing for homeless and employment stability.
3 minutes.
3 minutes, thank you. How they moved through to thinking about creative solutions through an impact effort grid, small wins, quick wins, which have bigger impact, to major projects, such as meaningful train routes to reduce traffic. And then they figured out how to actually get people involved in what the next steps would be through this build process, who were the key players that would be important, and moving forward with that process. They then presented these to county officials, and we had about a dozen county officials who showed up at the final presentations for the Photovoice and design thinking, and engaged in dialogue about next steps, about information, about resources, and how to move forward, actually engaging in adaptation processes. Again, similar but different specific themes as we moved across the 2 communities, again, showing the importance of really focusing on the specific communities rather than an entirety of a county. And many of these are about things that are much more easily accomplished than necessarily major infrastructure kinds of projects. Finally, to see whether or not these things actually work to increase community or individual capacity, we measured things like social connectedness, community engagement, individual agency, risk awareness, communication comprehension, and communication apprehension. A couple of caveats: this is a very small sample size. As we began this process, COVID shut down all of Miami the week we were supposed to go into the community, so we had to shift to online. That reduced the number of participants we were able to work with, and it also changed some of the nature of interaction. What we did see is threat perception did increase. They became more aware of the risks in their neighborhood. They also became more connected to other people in their community through this process. So those were both very positive. But some of the things like communication competence actually decreased. I think the challenges of using Zoom and the tools necessary were perhaps a little more difficult than was perceived, and especially when we're dealing with some challenges around disparities around technology, for example. Ultimately, I think what we saw from this is that we can do this kind of work online even during a pandemic, that the community-based approaches show that there are very different needs and perceptions and solutions by members of the community, that the government wants to be involved and have that connection with them, and that they've continued to move forward with that. And so we think this hyper-local approach is a different way to think about adaptation that may affect more of the day-to-day living as we deal with the long-term challenges that might come with retreat and increased sea level rise in communities like Miami. We've currently done this in 3 more communities, and we're starting to look at that data now. And I invite you to visit our website, hyloclimate.com, to learn a little bit more about the approach. Thank you very much.
Thank you. Perfect timing. Okay, so I don't see any questions on the chat, so let's go for the next talk. Next talk is optimal coastal protection against storm-induced flooding and sea level rise, accounting for stakeholder input, by Yuki Miura from Columbia University.
Can you hear me fine? Sorry, it took me a while to unmute myself.
It's great. Thank you.
Okay, great. So I'm Yuki Miura, a PhD candidate at Columbia University. I'm in civil engineering major, but we've been actually working with applied math and physics department and also National Center of Atmospheric Research in Colorado. So today, I'd like to talk about some part of our research. Okay. So since Columbia University is in New York City, our main focus has been New York City. And we are thinking to develop this framework first in New York City and then try to implement that to other cities. But right now, it has been always in New York City. So New York City, there is sea level rise projections. And this could be, of course, probabilistic, and especially we don't really know what's going to happen in the future. And I just want to kind of mention what is the projection here. So for example, in 2100, we have a low estimate of 38 centimeter. And also we could go to like higher estimate that could be like 1.91 meter. And that's a very big difference. And we, it's a very big difference. And then let me show you how actually they look like in the map in the city. So this is Lower Manhattan map. And we are plotting here Hurricane Sandy's actual inundation in the light blue color. And we also account for some of the sea level rise projection in 2050 and also 2100. And as you can see, as the color goes darker, the inundated area is expanding. So I have to note that here that we are using middle range estimate. So it's not like 1.9 meter in 2100 or 40 centimeter, but kind of moderate in between. So if we have higher estimate, higher sea level rise in the future, this projection here on the map could be worsened and then wider area would be inundated. So that was above ground, and we also have some simulation capability for underground. So we have MTA subway system in the city, and if you were around in the city in 2012, you have seen that basically Hurricane Sandy hit the area and subway system was not functional at all. And we also check what's gonna happen if we have something similar scale of hurricane with this middle estimate of sea level rise. And as you can see, on the left side, this is Hurricane Sandy only. And you can see that basically a lot of tunnel stations are completely flooded. But also if year goes and then sea level rise happens, and then we can see the tunnels, flooded tunnels are extended. And also we have more red dots. Red dots here indicate the direct flooded stations, means the stations which is in the area of inundated area, so that the station got basically flooded with its own openings like stairs or elevators. So what can we do for future storms and sea level rise? Because we kind of know that what's going to happen, and then probably we may have some big future storm as well. And as many of you here probably know a lot, maybe better than me, there are a lot of possible adaptation strategy protective measures. For example, we have here barriers. Also, we can individually raising the infrastructures, buildings, probably not in Manhattan, but maybe like a Rockaway area. And we can also do seawall, artificial dunes. Simply, we can also add some sands on the beach that could basically slow down the water speed. And of course, we also have managed retreat. And the difficult question is which strategy we should choose, because there are so many. And also, once we decide which one to implement, where should we implement that one? And also, when is the best timing to do this? Because maybe we need it right now, or maybe we don't need it right now, but later. And if that's the case, maybe it's better economically waiting for the time when it's actually needed. So basically our project is to figure out all these questions. So we define this optimal solution given a prescribed budget as a solution that maximizes reductions in losses, damages, income, maybe also interdependent economic losses. There are so many more. And also this solution can be a combination of multiple strategies. For example, maybe we can build seawalls in Lower East Side and maybe do the managed retreat for some other area. Or maybe we can do many more of the combination. And also it's very important to take into account of stakeholders' feedback, social equality, justice, and acceptability, so that once we figure out, cost beneficially, great idea, but maybe if people don't like it, probably we are not gonna end up have these strategies implemented. So it's really important to take into account of those inputs. And last but not least, we have to always consider about the future storms for future planning. And the important thing is here that future storms are never be the same. So for example, we will never have Hurricane Sandy as it was, maybe something similar scale, but maybe even bigger or smaller. So we shouldn't just stick with one hurricane event to plan something for the future. So we are using like millions of hurricanes that could potentially happen in New York City. And these are probabilistically modeled. So this is our proposed optimization methodology framework. As you can see, it's a loop, and we start from strategy. So we can parameterize the potential strategy you wanna try to implement, at least in consideration. We can try barrier, we can do seawalls, we can do managed retreat. In our system, we are trying to do more for like seawalls and these protective measures. And then if these things don't seem to work, then we are also combining managed retreat. Once we decide the strategy, we can also check what's going to happen with the hurricane in the future. So flooding estimation can be done with two methodologies here. We have a GISSR model and GeoGlow model. GISSR model is computationally very efficient, but it's more heuristic physical model. So it's not greatly accurate, but it's very good for like a fast, rough estimation. So we use this GISSR model for the first groups to find the potential optimal solution. And then once we narrow down the solution, we can move on to GeoGlow, which is based on finite volume method that's way more accurate, but slightly more computationally expensive, and to basically decide the real optimal solution. And once we analyze the flood estimation, we can also check the damage. And analyzing damage, we can use some fragility curves that's developed by our Columbia University team and also stakeholders' input, basically to convert the flooding height to loss of damage. And then once we have the damage analysis—
3 minutes.
Thank you. We can check the suitability of this current strategy by checking this cost-benefit analysis and also communities' acceptability, equality, and social justice. And these are based on stakeholders' interviews from New York City Mayor's Office, MTA, and there are some more agents in the city. And also we are going to talk to affected communities to hear what they are thinking as well. And if these requirements are met, that's great. But if not, we have to go back to strategy, parameterizing of strategies again to find the better solution. So we're gonna do, like, for example, we try the barrier, so maybe we're gonna do something like seawalls. And if everything met perfectly, then we can say now, okay, we have an optimal strategy, that maximizes reduction of loss given the budget. So this is a preliminary result of optimal load measure with its budget in Lower Manhattan. We are checking for this one for 2020 to 2100 over 80 years. And as you can see, if you have, like, for example, $500 million, the priority will be Lower East Side. And this would be the optimal location to put here. And then, of course, if you have more budget, then we can extend that. And as you can see, as long as you have more budget and more, the wall is going to be extended, and also it will be higher as well. So this is the summary. Today, I talk about our methodology framework for optimizing protective strategies. And then we have the way to estimate the flooding with GISSR model, GeoClo model. We convert the flooding height into loss in a damage assessment. And then eventually we check the suitability with cost-benefit analysis and also stakeholders interviews to find the optimal solution. So the future work we are thinking right now is considering more of environmental ecological concerns, social equality constraints, and importantly, managed retreat. We have to figure out what is the best way to quantify managed retreat in the optimization loop. And also we are thinking also to take account for the financial instruments like insurance, catastrophe bonds. And since it's gonna be very difficult optimization because it has a lot of constraints and various functions, we really need more sophisticated optimization schemes. And eventually we will apply this methodology for other cities. And they are my collaborators and mentors. And thank you very much. That's all.
Thanks, Yuki. That was a very good time as well. Everybody's being wonderful. So next talk is going to be by Maximilian Stiefel, Socioeconomic Risk Class across the Conterminous USA.
Hi, everyone. My name is Max Stiefel, and I'm from the University of California, Santa Barbara, where I'm a PhD candidate. And thanks for having me. Thanks for putting on this conference. I've really enjoyed listening to the talks in this session and in other sessions. So today I'll be talking about socioclimatic risk across the conterminous US, so the continental US. And it's mostly just going to be a high-level overview of some of the property level risk assessment that I've been conducting over the past couple of years, and then sort of comparing it to social vulnerability factors and seeing where we might observe some of the highest socioeconomic inequities with climate risk and social vulnerability. So just want to start with acknowledgements to the UCSB Department of Geography, and then I also work as a scientist for Climate Check, which is trying to provide open access, free information to individuals for property level risk assessment to climate sensitive hazards. So the outline of the talk, it'll be heavy on the climate risk measurement, and then I'll dive into a little bit of the social vulnerability index and then present some of the socioclimatic risk disparities and hotspots that we have been studying. So the hazards that I will be looking at today are extreme heat and precipitation, drought, primarily water scarcity, wildfire, and flooding. So we have 4 types of flooding: high tide, storm surge, fluvial, and pluvial. In general, when we estimate these climate risks, we will estimate the historical hazard exposure and then the projected hazard exposure, and then calculate the relative change from historical to projected, and then weight that relative change, or weight the projected estimate by the relative change and then produce relative risk ratings by mapping those values onto the CDF to get just like a relative idea of how risk spreads across the conterminous US. And we average all of these with any available climate model from CMIP5 that we have for the variety of data that we're using. So heat and precipitation comes from downscaled data called localized constructed analogs, and they're 5 kilometer squared resolution. So for heat, we only use the counts of extreme days, so basically the number of days over a historical baseline temperature value. And then for precipitation, we also include the exceedance magnitude, so that value at which days exceed to be considered extreme. So extreme heat we present here, and we see a lot of extreme heat. These are estimates for 2050, by the way. So we see a lot of extreme heat in Florida, and then parts of the Mississippi Delta, and then up the Mississippi, and also parts of inland Western US. And for extreme precipitation, we have higher scores in the east of the Mississippi, and in the mountainous areas of the Mississippi, or of the Eastern US, and then also in the Pacific Northwest and parts of the Rocky Mountains. For drought, we use something called the Water Supply Stress Index. So it's basically just a supply-demand hydrologic model for socioeconomic drought. And demand is just any sort of like withdrawal or consumption from the HUC 8, which is a watershed that is at the sub-basin level. And supply considers water flow and then interbasin transfers from different HUC 8s. And this is the risk rating that we've estimated. As we would expect, the rating is much higher in the Western US, except for parts of the Pacific Northwest. And for wildfire, we combine 3 different data products. So one is from MC2 dynamic global vegetation model, and that's to get our projected climate risk. And then we also use higher resolution data from the US Forest Service on wildfire intensity and severity. And we combine all 3 to create a 30-meter squared resolution risk rating for the whole US. And so just here we're presenting a bit of the risk rating for northwestern states and then for southwestern states. We also mask these wildfire risk ratings by land cover, so that densely populated urban areas, if they have mostly concrete, things like that, or agricultural areas wouldn't be considered as having fire risk, despite the surrounding risk. And then for flooding, we've used an open source 2D flood model that is at 30-meter squared resolution. And we've only modeled thus far for a 6-hour precipitation event. So this is just basically for surface water flooding, not for fluvial flooding. And most of the data comes from government agencies. And so you have a variety of sources. The most important, of course, is topographic data for inputting to the 2D flood model. And we also estimate the relative change in the magnitude of extreme precipitation events at the 1 in 100 and 1 in 500 return intervals. So a storm that would happen 1 in every 100 years. And then we apply these to intensity, duration, frequency curves, which basically give an idea of the relationship between the intensity of a precipitation event, how long it would last, and then how often it would occur. And so we see that a lot of the increase is happening around the Gulf states. And this is just an example of some of the output from these 2D flood models. This is around Philadelphia Airport. And then for fluvial flooding, we've just taken the FEMA data that is digitally available, and then we've also integrated a random forest-based floodplain that was fed data from FEMA as well to try and guess where floodplain would be if FEMA had mapped it, had a chance to map it. And it's also a 30 squared resolution. So an example of that data around Omaha, Nebraska. And then coastal flooding, primarily the data comes from NOAA. We have data from tide gauges and on mean high water, and then also relative sea level rise. Coastal flooding is typically divided into high tide and storm surge flooding. So high tide is basically just seeing how often the tide will exceed elevation for whatever your grid cell resolution is. And then we shift it by relative sea level rise. So by relative sea level rise in 2050. And then storm surge, we use some models from the National Hurricane Center to estimate depths, and then also look at observed hurricane tracks between 1900 and 2000 to estimate the probability. And an example of high tide flooding in Miami, as well as storm surge in Miami. So very quick overview of the climate risk data that we are using. And so we're trying to just understand how social vulnerability and this climate risk data that we are using compare. So the social vulnerability index is the main way in which we are studying this concept. And it was introduced by Susan Cutter in 2003 as a way to, to operationalize social vulnerability by using a bunch of different census variables. Not
3 minutes.
The details. Yeah, thank you. I'm not going to go into the details of the methods, but the general idea is just to aggregate all of the variables using principal components analysis. So this is an example of some of the variables and the spatial distribution of the social vulnerability index across the US. So just some bivariate associations with the social vulnerability index and heat. We see high associations in black, and those occur in parts of the desert Southwest and then the Southeast US. Also with flood, this pretty much occurs all over the place, but particularly in the Pacific Northwest and then in the Southeast. So we estimate a couple of climate risk disparities. One is the proportion of census tracts with high climate risk and high social vulnerability. The next is the relative difference in climate risk for high social vulnerability populations. And then the third is the relative difference in the probability of experiencing high climate risk for high social vulnerability populations. And the second two are based off of the national average for low social vulnerability populations. So the proportions are pretty similar to the maps that we saw before with the bivariate associations, because it's just the proportion of census tracts within counties that have both high SOVI and high climate risk. And then this relative risk disparity, where we're comparing the risk rating, the value experienced by high social vulnerability populations to the national average for low social vulnerability populations. You can see that there are high socioclimatic risk counties all across the US. For example, in Kings County, some people experience nearly double the average wildfire risk. And then for the probability of experiencing high risk, we see the same spatial patterning. For example, in Shiawassee County, people are high social vulnerability people are 3 times as likely to experience high flood risk. And we also did some spatial clustering to look at the patterns, and generally when there are large area patterns, such as the Southeast or the desert Southwest, we also see statistically significant clustering of these 2 variables. And so kind of just the takeaways are, not too far from what you would imagine, but in terms of high socioclimatic risk, we see it in east of the Mississippi River and the Pacific Northwest for storm and flood, in the desert Southwest and Southeast for heat, and then in rural areas west of the Rocky Mountains for fire and drought, and then rural inland areas west of the Rocky Mountains, coastal tracts in Gulf states, Appalachia, and central to southern Florida for an aggregated climate risk as well, which we didn't present, but just averaging all the climate risks together. So just kind of the main considerations we would like to provide are that counties with the largest disparities exist pretty much in every state, but they do vary by the climate risk and by the social factor, as would be expected. But age has appeared to be eminently important in this analysis. So thank you.
Thanks very much. I'll have to move on. Next talk is Tropical Cyclone Risk Modeling by Adam Sobel, also from Columbia University.
Hi, the previous speaker could release the screen share. Thank you. Okay. Desktop. And hopefully you can see that. So just to acknowledge my co-authors very quickly, in the interest of time, I'm not going to name them. This is Tropical Cyclone Risk Modeling. So in making decisions about managed retreat, this is probably the only time in my talk I'll mention it specifically, but we're thinking about basically any kind of climate adaptation. In general, we think that these decisions, among other considerations, should be informed by some kind of scientific assessment of what the underlying climate risk is. After all, that's why we're doing the adaptation. And in a lot of cases, a big part of the risk that matters is risk of extreme weather events. So things that don't happen every day, but that have a big impact when they do, and whose probabilities or severities might be changing. So how do we think about extreme weather risk, and how do we characterize it? How do we assess it in a changing climate? That's what we're interested in here. So there's a few ways you can do this. You can look at the historical record. And the great thing about that is it's real. You know, you're looking at real events, no model errors to worry about. But the downsides are it's the historical record in most places for most kinds of events is too short to capture the full range of events that you might be interested in. For example, you know, what's the probability of a Category 3 hurricane hitting Boston? It's never happened, but the probability is not zero, and it would be catastrophic. So the historical record isn't good enough for that. And also the historical record is from the past by definition, and so it doesn't characterize the risk in the present and near future well enough in a changing climate. So we can use climate models, and the great thing about those, they're based on physics. They can predict climate change as well as we know how to do it. But the cons are that for some kinds of extreme events, at least, they're not captured well in climate models because resolution isn't good enough for other reasons. And that's particularly true for tropical cyclones, which I'm talking about today. Climate models are also expensive and complicated to use. It's hard to generate very large sets of synthetic events that you want to characterize risk. And they have systematic errors, and they don't explicitly represent the human impacts that events have. So what's been used in insurance industry is something called catastrophe models. And now in other contexts, but they're developed by the insurance industry. And here's a slide from our colleagues at Aon that gives a sort of schematic of what a catastrophe model is. So the part that has a hazard, that's however you represent the geophysical events themselves. Then vulnerability, here really exposure and vulnerability. Exposure is what are the assets at risk, and vulnerability is how much would they be damaged by a given level of hazard. And then there can be other components in insurance that go all the way to characterize insured financial losses and so on. But a limitation for our purposes, one limitation is that although the historical event catalogs, basically synthetic events, go beyond the historical record, but they're closely based on the historical record using statistical algorithms, basically a bootstrapping. So they don't represent the physics of climate change, and they don't characterize that change generally. There are also the models developed in industry, which is mostly what is used, at least in the insurance industry. They're mostly proprietary, so they're not, not debated in the peer-reviewed literature, and they tend to be developed for specific countries, and generally for those where there's a lot of insurance. So if you want to work in poorer countries that don't have a lot of insurance, you're generally out of luck. And a particular challenge is for doing the exposure and vulnerability. in the insurance industry, those come from the the insured clients, but in places where there isn't a lot of insurance, it's harder to get to characterize vulnerability and exposure from publicly available data sets. So we want to do catastrophe modeling in academia. A few groups around the world are doing this, a growing but still small number. And the advantages are, as typical of academic work, it's open source. We can argue about it in literature. We can include more physics to deal with climate change. There are costs to doing that, but anyway, we can do it. We can work globally, and we don't have to be limited to where there's insurance. And in our particular group's case, we've been building a model for tropical cyclone risk. We've had the hazard component that describes the storms themselves working for a couple of years now, and we're just starting to work with exposure and vulnerability, and I'll give examples in a moment. So our model is called the Columbia Tropical Cyclone Hazard Model. CHAZ is the cute name we give to it, and an example of how we would use it in a climate change application is here. You'd have some emission scenarios like in CMIP, and you put those into a climate model, and then you simulate the climate. So all of that is not our work. This is coming from the CMIP or IPCC processes. But then we give it to our model, CHAZ, which looks at what the climate is, and based on a statistical dynamical algorithm that I will only very briefly sketch in a moment, it produces its own synthetic tropical cyclones. Here's some synthetic tracks that are consistent with that climate by the rules that we use. And so you could have observed tracks, you could have tracks downscaled from historical climate model runs, and then you could do some projected future. And then you could look at the difference, for example, to see the change in tropical cyclone risk. You could also just, instead of using climate models at all, you could just put observation-based data sets in here for the climate drivers and get a set of projected tracks that are consistent with the historical climate if you want to, and I'll show examples of that as well. Here's some equations. I won't really explain them. Here's our model developer, our lead person who really built this model, Jiaying Li. And all I'll really say is it has three components. We simulate the genesis or development of storms, the track or how they move, or the intensity and how strong they get. And all those are based on not really the laws of physics, but statistical rules based on historical relationships from between observed storms and the climates in which they occurred, plus a stochastic component that gives us the full range of extremes. So, but the main point is you do have to tell the model what the climate is. So there's some variables here like relative humidity and sea surface temperature that that you have to give it, as well as others. Here's a picture really quick. The bottom is observed tropical cyclone tracks from a few years, color-coded by intensity. The top is from the model. There's some systematic differences, and we have to bias correct those for some applications, but at least you give it an idea. It's not too bad. And I'm going to spend the rest of the time on a couple of applications. Oops, I've lost my, on a couple of applications. So here's the first sort of applied paper we did. This is estimating tropical cyclone risk in the city of Mumbai, not including climate change for this study. We did it based on historical climate, but Mumbai is a city that's very vulnerable to tropical cyclones, but almost never has them. So it's kind of an interesting case because if one happened, it would be really bad, but the historical record doesn't characterize the risk. So we used our model and another one from Carrie Emanuel at MIT, that's the blue, whose work inspired ours years ago. And we can estimate, for example, that this is a return period curve. So you can estimate, for example, that 100 knot, which is a US Category 3 storm, getting within 150 kilometers of Mumbai, that's what this plot shows, is an event with a 500-year return period, 1 in 500-year event. That's in the historical climate. We think that risk is getting worse, although in our work we haven't characterized it. Our main point of writing this paper was just to sort of get the attention and say that Mumbai is a place where people should be worried about tropical cyclones, even though they tend not to happen. And it turned out to be more prescient than we expected, because right after we published the paper, they had a very near miss, Cyclone Nisarga in 2020. And this year, Tukte grazed past Mumbai, causing some bad weather on the way to Gujarat province. So our work got some attention because of that. That was purely on the hazard. Here we're getting into risk properly. So this is work with our colleagues at Aon, a reinsurance brokerage firm, where they've used our results to characterize possible changes in losses in the near future, sort of 2040 time frame, due to climate change. So this is taking our results for hazard and putting it through their proprietary representations of exposure and vulnerability to get changes in actual loss. And I won't, this is I won't say anything more about this. These show sort of modest increases in losses by 2040, but I will, for different parts of the US, but I will come back to what one of the main uncertainties in this, which isn't fully described in this slide. The last application I want to talk about is work to characterize wind-related tropical cyclone risk for the Philippines. This is work by our postdoc, Jane Baldwin, about to be a professor at UC Irvine. So we use CHAS to make or observations to look at to get hurricane tracks. Then we have a parametric wind model that gives us actual wind fields across the Philippines. And this is work with the World Bank, which is just a test case. We picked the Philippines for a variety of reasons. And we have a
3 minutes.
Thanks. We have a representation of vulnerability. This is not social vulnerability. It's just fraction of assets damaged for a given wind speed. And there's a threshold here at which value this curve rises, and that's a tunable parameter. Then exposure, I won't explain how that's done, but it's a large national data set downscaled by our Swiss colleagues with population and nightlight data. And from putting all those together, we can get return period curves for losses. And this is from CHAS, this is historical, Haiyan caused huge damage. And you can go all the way to assess risk. And just to say that our colleagues, Brian Walsh is our colleague, an economist at the World Bank that we're working with. They have a methodology for going beyond asset losses to consider the fact that a dollar means more to a poor person than to a rich person. And they can look at losses of well-being rather than just raw dollar asset losses. And one of the conclusions from this work is that we should use not national level vulnerability. Here we tune the vulnerability curve to get observed losses from the EMDAT database. And we found that to get good results, you should do that using at a subnational scale. So why don't I just skip how this is done and go all the way to the results. This is comparing simulated damages to observed damages for historical storms. And let's focus on the measure on the right. This is a measure of agreement between all our storm damages and the observed ones. And you want it to be close to 1. And you do better if you fit the vulnerability curve region by region within the country rather than at the national scale. That's what we've done here. It's basically Manila has stronger roofs than the rest of the country. And we can assess that. We use household survey data from the World Bank to characterize the strength of the roofs. Last science slide. This is something that applies to all our work with climate change. This is a result from a paper led by Jiaying Li a couple of years ago, where we downscaled CMIP5 results. And this is the number of tropical cyclones across the globe simulated by our model, downscaling 5 different CMIP5 models going out to 2100 under the RCP 8.5 scenario. And you see some solutions increase and some solutions decrease. It's not because of which climate model you downscale. It's because of difference in 2 different ways we construct our model. And the difference is how we represent the humidity field in the generation of the storms. And there's 2 ways of doing it: relative humidity or saturation deficit. And they are indistinguishable in the present climate, but they give very different results in the future climate. We think that is representative of the actual state of uncertainty in the field more broadly. And so this is just to say that a lot of the ball game in this, certainly in tropical cyclone risk, if you think out this far into the future, is about explaining uncertainty. We cannot make like really confident predictions, but we can characterize the uncertainty. And I think that's maybe generic to a wide range of forward-thinking climate adaptation projects. So just to finish, I don't have a conclusion slide. I'm just going to say that we're very aware, as we've been talking more to social scientists, of the limitations of our top-down approach. That's very much what this is. And I'm quoting here from a recent paper by our conference organizers and a couple of co-authors. I won't read this. I'll let you do it. But here's also a quote from our postdoc Jane, as well as her student Katie Baldwin, who've written a book chapter on different ways of characterizing vulnerability. It's just to say that we are very much taking a physical science approach, trying to do something that can be where we can compare countries globally, but that comes at a loss of a lot of richness that comes from considering the real human beings living in a place. And we're very aware that ultimately one needs to combine both of these, and we're thinking about how to do this in our work, but that's in the early stages. So I will stop there. Thank you for your attention.
Thanks, Adam. I think we have to move on. Last talk of the session: understanding the impacts of managed retreat and resettlement on informal communities in Puerto Rico. Monique Lorenzo-Perez, please.
Yeah. Hello, can you hear me okay?
Yes, great.
Well, hello, everyone. My name is Monique Lorenzo-Perez, and I'm a recent graduate from a master's degree in city and regional planning from The Ohio State University. My colleague, Santina Contreras, was unable to join us today, so I will be taking over the presentation. And I'm going to be talking about our preliminary findings for a project titled Understanding the Impacts of Managed Retreat and Resettlement on Informal Communities in Puerto Rico. This is a qualitative study divided in 2 phases. And the first phase consisted on phone calls and structured interviews with planners, architects, among other relevant contextual experts based in Puerto Rico. This phase also incorporates a flooding risk exposure map for 2 informal communities in Puerto Rico. And the second phase focuses on the community's perspectives and experiences regarding exposure to risk and relocation and resettlement initiatives. The second phase consisted of focus group discussions, and it was conducted virtually. Both phases were modified to be virtually or remote because of COVID-19 restrictions. So just to have a general geographical context of Puerto Rico and its informal communities, Puerto Rico is a small archipelago, part of the Greater Antilles, located in the Caribbean region. And for those of you who don't know, Puerto Rico is a USA territory. So informal communities in Puerto Rico have a long history. Informal communities formed in a variety of ways. Those located in urban areas typically formed as a result of rural and urban migration period around mid-20th century. And this large migration led to housing shortage, and many communities, as a way to resolve this issue, established housing in unwanted, risky, and undeveloped lands. So relocation and resettlement practices in informal communities have taken place in different ways, such as targeting housing issues and moving them to public housing as a post-disaster response, as it was the case of Mamella's landslide, that is also known as a disaster-induced displacement, in the context of environmental health and hazards. And most recently, relocation and resettlement initiatives have been taking place as a mitigation technique to avoid or diminish the impacts of climate change, flooding, and other natural hazards. So you might notice that I'm constantly talking about informal communities and relocation and resettlement. So informal communities is what most of the literature and past research refer to as informal settlements. For this project, we're using informal communities because I think it adds more the humane dimension of it, that we're really talking about people and community ties, not just about the buildings. So when I'm talking about managed retreat, I'm referring to as a mitigation strategy, right? And relocation and resettlement as a technique, as of the way of how we implement the managed retreat. So the study also draws from the risk and consequences of managed retreat and relocation and resettlement literature. So when we jump into what we're looking to answer with this project is more to look into what the decision-making process looks like for informal communities in Puerto Rico, and how this hazard risk exposure impacts resettlement and relocation practices, and how informal communities are being engaged in the process. So in this first phase, we noticed that planners recognize the key issues caused and associated with informality. And this is an important component. We found that planners relate the issues associated with informality to natural hazard risk exposure. For example, in terms of housing fragility, planners identify that fragile housing places their resident at risk in the event of a hurricane. And it can be exemplified by this quote. Also, we found that some of the reasons and motivations used to initiate relocation projects include that we have communities living in risky areas such as floatable lands. Another factor motivating relocation is when other in-place mitigation strategies did not appropriately mitigate the existing hazard, for example, seawalls. We build a seawall, it breaks, it falls down, then we need to build another one, and then it falls back again, and they're like, people will be, okay, so we need to retire, like we have to move people out of here. And another layer that adds to this issue is that idea that in low income and informal areas, it's not really cost effective to invest in protection. And one of the participants stated that it could be that the cost to protect the community is just too much, in which case it would be necessary to relocate, which is a sad thing to hear. Other planners also mentioned that severity of a threat or how imminent the danger is also pushes motivations to relocate. So when planners and decision makers eventually decide to relocate an informal community and they think it's the best option, the common reasoning and expectations is that a safer location and a better housing can be provided, particularly in the context of managed retreat. They could be safe in the face of a natural hazard in the new place, right? And there's a quote from a participant that says, like, they should be safer, right? They should be safer in the face of natural hazards in the new location. And well, here's where things get a little bit more complicated. There is a perception that the relocation process is being done with the intention to mitigate a specific risk. But what happens when other risk or even the same risk becomes present in the new location, particularly considering the impacts of climate change, right? And there's an exemplary quote here that says that on many occasions, as you don't look at all the risks, the area is again at risk from climate change, right? So there's a lot of variables that we have to keep an eye on that could affect the new resettlement area that we're trying to move people to. For example, in the case of Villa del Sol, which is an informal community located in Toa Baja, Puerto Rico, it went through a relocation and resettlement process. Still, they experienced flooding in the new location, even when the new land was considered to be safer than the previous one. One participant explained, it's less floodable than the other land, but during Hurricane Maria, there were areas that had flooded up to 4 feet. Right, and we can see that there's still this notion that, you know, they're not as exposed as before, which can be problematic because the real idea behind managed retreat is to move people out of risk, away from the risk. And leaving them at some level of risk is not the real goal of relocation and resettlement initiatives in informal communities. Similarly, we have the case of Vietnam, which is an informal community located in Guaynabo, Puerto Rico, that also went through a complicated relocation process. Besides, also, they were moved to a place still at risk. The community member was not informed of what really happened, creating confusion and skepticism towards relocation practices. And a community planner shared with us this sad experience where people were asked to sign papers, not being educated as to what the paper said. And, you know, before they knew it, they agreed to relocate. And just to show a little, explain a little bit the map so you have an idea what I'm talking about, this yellow portion right here of Villa del Sol was the previous location. And this northern region right here in green is the new location where they're being resettled. So we can see they're outside mostly of the flooding zone area, but still they experience flooding for Hurricane Maria. And that's why we're talking about here that I'm really moving them to a completely safer area. So because of the time limit, let's jump into the second phase. And so at this point, until this point, we talked about what planners are saying, right? What they understand and what they have a vision for in terms of managed retreat and informal communities, experience with relocation. So let's jump now into the preliminary results of the second phase. And in the second phase, we found that community members are fully aware of the risks and living conditions that they're being exposed to in their communities. Risk exposure, informality issues, and the severity of the threat do motivate residents to consider relocation. But other factors influence the decision-making process, which eventually leads them to resist relocation and or wanting to stay within their communities. Some of these factors include place attachment, and this is a place where generational families are settled, right? This is their place, and you can read the quotes of what community members shared with us, right? Also, we have this initiative of making local mitigation efforts, right? In the case of a hazardous event or a risky situation, local mitigation efforts take place in order for them to stay in their community and avoid relocating. So we should rethink about in-place mitigation investments these people are willing to make it work, right?
2 minutes.
Thank you. And there's this last piece, and it's the fact that informal community members feel like there's a lack of communication and or misinformation about the real opportunities that come with managed retreat practices, which creates confusion and skepticism towards relocation initiatives. And we're close to an end, but I wanted to make emphasis on the fact that the community members who participated understand the risk and the issues associated with informality. There was a general agreement among the interviewees that if residents who live at risk in informal communities are offered the opportunity to relocate to safer areas, they're likely to agree. Many of the residents have not left the community because they lack the resources to do so. So we could be more aware of what safety in the new location looks like and how we're really incorporating the community in the planning process to facilitate managed retreat practices in the future. And that's all that I have for today. Thank you so much.
Thank you. I don't see any questions, just a comment. Greetings from Puerto Rico, from Laura Cabrera. So I think we should move to the question and answer part of the session. So we already have a couple of questions. A few of them have already been answered by Tyler. So I think I'll move to the ones that are already there and have not been addressed yet. So there are 2 questions for Yuki. Yuki, first question, have you considered a combination of strategies and not one by one? And how hazard exposure models and are changed for considering the effect of such strategies?
Sure. Thank you for the question. So the combination, yes, we have considered. Today, I only showed the preliminary one, so it was only seawall, but we can do like seawalls or elevating somewhere, artificial dunes, we can rise buildings, and also we can seal like openings for subway systems, like we have stairs, manholes, all these things. And this can be combined, and that's more, yeah, I think meaningful. Just the one problem is how we are optimizing right now is almost like we are checking all the possible strategies and then pick the best one. And we also try like coordinate descendant, but if we have more combination, more possible options, it's gonna be just like really exponentially larger problem. And so if we don't really sync up all the time, we can do basically anything. But yeah, right now I think computation time is a problem. So we have to find more sophisticated optimization scheme to do more like meaningful but effective way. And the second question is the exposure models. So our input is a storm surge model. So unless you change like coastal line, I believe it's not gonna really change. The storm surge data will be the same. But we always calculate the flooding and what's gonna happen to the city. So of course, if we have a seawall or something like sealed openings, then the damage cost will be completely different and the flood area should be like smaller as well. I hope this answers the question.
Yes, thank you. So if the audience has more questions, please send them in so that we can ask the speakers. There were a few questions for Tyler. He answered on the chat, but maybe he wanted to, you could answer, summarize them for us?
Sure, I'd be happy to. So let me start by saying I'm not the GIS person on the team, so my answers are not as comprehensive or perhaps as knowledgeable as they should be. But there were some questions asked about specifically the surface temperature and whether or not that reflected kind of the real living temperature in Little River, where we saw temperatures of 136 degrees. And my understanding of that data is that it's measured a specific distance from the ground, and that's what that reflection is a reflection of. And that even if you go up by a few inches or a foot, that temperature is going to feel less extreme as you move farther away from the surface of the Earth. At the same time, when we look at some of those extreme temperatures, we know that they're in places that are pretty much exclusively built out in terms of concrete and asphalt and very reflective of that heat. And that's oftentimes where things like the public transportation hubs are, and people are sitting there with no shade suffering through that. So I think there's a degree of both parts that are happening as part of that. The second question was about some of the data sources, and most of the data that we have is publicly available data. Air conditioning data specifically, I believe, came from Esri, and another one that I had posted in the chat, GRI. But our data sources came from a variety of different places, and I would have to get into the data library and probably refer you to our GIS person to give a more specific answer to that, which I'm very happy to do. I put my email up there, and if anyone wants to know more about that, I can put you in touch with our GIS person and go through more about where that data comes from and the processes of transformation that we've used as part of that.
That's great. Thank you. We have a few more minutes, so I would like to open for the speakers to, make questions to the other speakers or comments about their talks. Please go ahead. Someone?
Actually, I saw one question from Rodley. Maybe I can address that quickly.
Okay, please.
Yeah. So yeah, it was a question for spatio-temporal relationship. Maybe it's a little bit similar to the answer I just said, but yeah, we consider a strategy. For example, if we construct something in 2030, then after 2030, all the area behind it will be protected. So we have a temporally different solution. And if this affects retreat option, yes, I think. So if we can also add the seawall on top of it, if the sea level rise looks really bad, but if that doesn't make sense, cost beneficially or some other reason, and then we can start thinking about managed retreat as well.
Thank you, Yuki. Other speakers have any comments, questions to the other speakers?
Got a question or comment for Monique. So when we started our particular project, we were really interested in the sense of community that you're talking about in these informal communities and how people are perhaps culturally tied or tied to family members and very reluctant to move. And we've seen a lot of communities in Miami disrupted that way, but we haven't seen as much in what we've been doing with our participants about feeling that strong type of connection, except in a very few spots. And so I just wanted to say, I found that very interesting that you're finding that there, and glad that you're bringing those kinds of issues to the forefront. It was really interesting to hear about.
Yeah, thank you. And if I can add a comment on that, I feel like in the case of Puerto Rico and informal communities, many informal communities established in rural and urban areas have been historically there. So we're not just talking about a community that appeared a year ago, we're talking about communities that have been existing for more than 10 and 20 years. So there are a lot of generational ties and a lot of experiences that make them feel attached to the place. So I feel like that's a factor affecting their place attachment.
I would also have a question for Monique, if that's okay.
Sure, go ahead.
Thank you. Having worked with informal settlements myself, I came into the field work with a very sort of distinct mindset, and then after working with these local communities, I had to rethink this because I thought, of course, informal settlements would be the classic case of being the most vulnerable communities. But actually, I found that in some senses, they were actually also remarkably resilient, certainly in terms of innovation and being able to adapt to difficult circumstances. So I was just wondering if you had similar experiences in working with communities on the ground in Puerto Rico.
That's a great question. Well, sadly, I wasn't able to visit the community underground because of COVID, but we did manage to do focus groups. And I think that was really a good way to reach out to them and learn about their perspective and experiences. And I will say that they're really eager to strive, and they're really eager to endure the hardship that comes with risks. And particularly this community ties and community bondage is really strong. And I think it has to do with being there for so many years, but also our culture and the type of people that we are. Like it encourages this auto-management, like self-management process of trying to do things that works for us and works for everyone. So it is really refreshing to see these people in these communities wanting to do better for their communities, but also it is really sad to see the conditions that they're struggling with. And as planners and as a planner, I really want to help that sort of scenario that they're tied in. So yeah.
Thank you.
Thank you. We have time for one last question. Is anybody has one last question? I have one. How people are interacting with the local government, how do you deal with the issues of changing government and change priorities? So you have one mayor that goes with your ideas and change, and then you have the next one that doesn't support them. How do you deal with that in your projects? Maybe David, how are you doing that in Miami?
Yes, I can say a bit about
sorry.
that. It's one of the key challenges, of course, because you have differential timelines. So when we talk about climate change, we're talking about everything from about sort of 30 to 50 years, and political mandates, which are normally, when we're talking on the mayoral level, we're talking about 5 years. So it's really difficult from a political perspective to get politicians to plant olive trees, we always say. One way to do it, of course, is to try and strengthen NGOs to put pressure on the political process and to use community-based platforms of people who are affected by these decisions in the long term, and not just politicians who have different interests as well. But it's really difficult.
Thank you. I think that was such an interesting session. Excellent talks. Thank you for all the speakers for participating, and see you soon. Bye.
Bye.
Thank you all.